Welcome back everyone, and thank you for joining me. Let's continue with another example of analyzing a polynomial function. This time we are given g of x equals negative x plus 5 times x minus 1 squared. Let's analyze this function together. We'll begin with the domain. Since this is a polynomial function, we'll say that the domain is a set of all real numbers. Now, let's determine the range. To do this, we first check the degree of the polynomial. As you can see here, we have a factor of x plus 5 of multiplicity 1 and a factor of x minus 1 multiplicity of 2. So we also have a constant factor here, negative 1, but this is degree 0, so we do not take that into account when calculating the degree of the polynomial function. So we'll say that the degree would be equal to 1 plus 2 or 3. So this tells us that this would be a polynomial function of odd degree. Now, since this is an odd degree polynomial function, we'll say that we're ready to determine the range of it because all odd degree polynomial functions, for reasons that we have discussed in multiple videos, will have the range, the set of all real numbers as well. Now, next, we'll determine the x-intercepts. Remember that at the x-intercepts, the value of y equals 0. So what we do is we set the value of y, or in our case, g of x equal to 0, and try to solve the equation for x. When the equation is given in factored form, it's fairly easy to determine the x-intercepts. So we have 0x plus 5 times x minus 1 to the power of 2. So we're going to set x plus 5 equal to 0 and x minus 1 equal to 0. So that will give us the x-intercepts at negative 5 and another x-intercept at 1. So we're going to write down the intercepts in here, just list the information on the table. Now, we have the x-intercepts at negative 5, 0, and another x-intercept at positive 1, 0, or we can simply write x-intercept equals negative 5, separate them clearly by a comma, and then 1. Next, we'll determine the y-intercept. So, for the y-intercept, remember that we're going to set the value of x equal to 0 and then evaluate y. So let's write this down in here. So what that means is that, in other words, we have to find g of 0, which will be 0, 0 plus 5, and then 0 minus 1 squared. So this would be 0 times 5 times negative 1 squared, or simply negative 5. So the y-intercept is negative 5. So we're going to write 0, negative 5 for the y-intercept, or you can write y-intercept equals negative 5. Now, next we'll have to determine the intervals of increase and decrease. Remember that intervals of increase and decrease are related to maximum and minimum points on the graph. So we'll need to know what the local min and max are on the graph, and maybe absolute max and absolute min. So these are the points that we need to find before we determine intervals of increase and decrease. Now, since we're at it, now recall that because this is an odd degree polynomial function, there won't be any absolute min or max. And the reason why is because only even degree polynomial functions are able to mark a maximum or a minimum on their graphs, because due to the nature of their end behaviors. Now, absolute maximum will be none then. So since we're here, let's clarify this as well. And there will be no absolute minimum either. So we are going to determine intervals of increase and decrease once we determine the local min and max. So next, we will find where the intervals where y is positive or 0 or negative is, and the rest of the information. But before we move on, let's pull down the information we already have. So what we have is the x-intercepts. We have one x-intercept at negative 5, one x-intercept at 1, and we also have the y-intercept at negative 5. And we also know that this is a third degree polynomial function, and we can in some ways predict the end behavior of it if we looked at the coefficients. Remember that for the coefficients, we look at the coefficients of x in each factor and other constant coefficients that the function may have. So when you see a negative sign in here, it means that there is a factor of -1. So the leading coefficient will be equal to that -1, which is one of its factors, multiplied by 1, and then multiplied by this coefficient 1 to the power of 2. Now, obviously, 1 part 2 is 1, so we don't really have to be that detailed when we determine leading coefficient, but please be mindful of the fact that when this coefficient is a number different than 1, then that will change the leading coefficient if the power is different than 1 here. So we have -1 times 1 times 1 squared is -1. So we have a negative leading coefficient, all degree polynomial function. So the behavior will start in quadrant 2 and end in quadrant 4, just like the line with negative slope. So at this point, I would say that we are somewhat ready to sketch the graph. This is not an accurate graph. We're going to cross the x-axis through at -5 because it's a first order root, and then we are going to come back here at the y-intercept, get ready to touch the x-axis again, but at x equals 1 it's a second order root, so that means we are going to try to make a turn in here. So this will be a sketch of the graph, definitely not the actual graph, because we still need to determine the value of the local min and max. But drawing this will enable us to answer quite a few questions here on this chart. For example, we can determine the intervals where y is positive or 0. So in other words, when the graph is above the x-axis. So graph above x-axis. Now these are things we already know, but I'm just writing them down as reminders. And here we have the graph below the x-axis for y values less than 0. So let's trace all the sections of the graph where the graph is above the x-axis. So I see that the graph is above the x-axis right here and nowhere else really. But this would be above or a 0, and here is just a 0. And the rest of the graph will be below the x-axis. So we're going to say that the function will have a value that is positive or 0. Anywhere for the x values, you can see that this graph exists in this domain for this function, so from -infinity up to -5. Now we do want to include the -5, and the reason why is because we are looking at y values bigger than or equal to 0. So -5, -infinity to -5 is the first section where the function is positive or 0, but also the function is 0 at x equals 1. So, and you're gonna join to this, right, a point with coordinates x equals 1 and y equals 0. So another way of writing this, if you wanted to use in interval notation, then you can write 1 to 1. So that means that only this point is included in this particular interval. And you have to use the square brackets, obviously, because, you know, this is the number included in it. Now, the graph will be negative anywhere from -5 to +1. As you can see, the y values are all negative, and the x values responsible for these negative y values are between -5 and 1. So we're going to say that the x values between -5, 1. And again, we're going to have this interval be joined by this next 1. So that's from 1 to -infinity. So 1 to -infinity. So as you can see here, we have to leave 1 out, right? So even though it looks as if the function is decreasing or is below, no, it's below the x-axis, or it's negative throughout the entire domain, please do not include the 0. And it's one of the tricky questions where students often lose marks this is called attention to details. Now, I think we can move on now to end behaviors. We do know what the end behaviors are. You see that on the left end, where x is approaching negative infinity, the y values are approaching infinity. So on the left end, we're going to say that the y values are going up to infinity. And on the right end, you see that the y values are going deep down to negative infinity. So we're going to write negative infinity here. Now it's time for us to determine the intervals of increase and decrease. Now for this, we're going to need to locate or to find the coordinates of the local min and local max. So far though, we know that the graph of this function will pass through these points. I'm going to try to make this graph color, I don't know, we'll make it blue. So the graph is coming from the second quadrant, hitting the x-intercept here. We don't know how far down to go, and that is a point we need to work with. We do know that the graph will pass through y equals -5, and it will touch the x-axis at 1, which means that this is the path that we know, and we can continue drawing the graph this way. So the section of the graph we need to work with right now is only this one, and we need to find the local minimum. Now remember the strategy we used in the previous example. So from -5 to +1, we want to find a point somewhere in the middle. Now it is very interesting when functions have double zeros. They usually, the minimum tends to be a little bit more skewed, closer to the double zero, but let's check and see using our traditional method. So we're going to pick a number anywhere between -5 and 1, and I am going to choose in here the -2.1, 2, 3, 4, 5, 6. So we have 6 units, so halfway we're having -2 as our central value. So -2 is going to be our helping number, and we're going to have to find the value of the function at -2. So start with g of -2, so that's negative. And then wherever you see x will be replaced by -2 plus 5, and -2 minus 1 squared. So that will give -3 times -3 squared, which will make a 27 negative. So we're going to say that when x equals -2, the value of y is -27. This is definitely a point worth plotting on the graph because it is a point on the graph of this function. Now remember that according to this scale in here, we're going to gently kind of scale it in here. So it's going to be a point somewhere in here. All right. Now the point is, does the graph of this function go down here and further down and goes up, or does it actually, go down this way or on the other way around? So in other ways, we need to check and see the left side and the right side, because it can go down on the right, further down on the right, or it can go further down on the left. So I'm going to leave both of them in here so that you can tell what my point is. So both graphs will pass through this. So for this, we're going to go to the left and to the right of -2. So I have a feeling that it's going to be towards the negatives, and I'll explain you why in a bit, because it's not just a feeling, there is some reasoning to it. So we're going to have to check this at -2.1, and what we are looking for is smaller values than -27, because we're checking to see if there is any lower value in this direction. So we're going to use a calculator for this. All right. And we'll have -2.1 plus 5, and then -2.1 minus 1 squared. So that would be equal to, now -2.1 plus 5 would be equal to 2.9 positive, so -2.9 here. So this is this negative sign, and this will multiply negative 3.1 squared, so negative 3.1 squared. So if you multiply by negative 3.1 squared, then we will get in here negative 27.87. So what that means is that the function is indeed going further down for x values that are less than negative 2.1. Now, remember how I said that I have a feeling it's going to be lower in here, and that is because when you have a double root, the function will make the turn pretty quickly. So probably they're making the turn, a little bit further from the middle between the x-intercepts in this direction, because they are very smooth graphs, right? So they don't just abruptly increase. So they cannot have, the graph cannot go very fast in here and then make a turn very quickly. So we are going to continue digging deeper to the left to see if we can find smaller or even smaller values of y. So we're going to go for g of negative 2.2. And some people are very, risk takers. And follow a risk-taking strategy by going even negative 2.3 or negative 2.4, because it can be that we are far away from the really for the lowest minimum. So negative 2.2 plus 5 and negative 2.2 minus 1 squared. So let's check and see what happens in here. So we have a negative and then negative 2.2 plus 5 and then negative 2.2 minus 1 to the power of 2. And what I get in this case is negative 28.67. So negative 28.67, that's quite a number. So it's almost 1 unit far from this. So it seems that the y values are changing kind of by a lot. So what I'm going to do is I'm going to try negative 2.4. So negative, so we have negative 2.4 plus 5. And then negative 2.4 minus 1 to the power of 2. So negative 2.4 plus 5 multiplied by negative 2.4 minus 1 to the power of 2 will give negative 30. So negative 30 is quite big of a difference in here. So I'm going to continue at negative 2.5. And again, these are calculations that you don't have to show, not all of them at least. So you can just do them on your calculator and then figure out which numbers you have found. But I would keep note of the what values I've tried and find what value I'm finding for y, so that I won't, by accident, double calculate the same number. So let's check and see. I can even try negative 2.6. Let's try that. So we have negative 2.6 plus 5 multiplying negative 2.6 and then minus 1 to the power of 2. And we see that we get even a smaller value of y of negative 31.1. So, but I do see that when I go 0.2 from 0.2 smaller, so from negative 2.4 to negative 2.6, the differences do start slowing down. So I'm thinking that maybe negative 2.8 will be my last, jumping number here. So negative 2.8 plus 5 multiplied by negative 2.8 minus 1 to the power of 2 will give me negative 31.7. So negative 31.7 is a smaller number, so this is a lower minimum. So we're going to go at negative 2.9 this time. Let's see what happens. So hopefully it's going to stop soon. Negative 2.9 plus 5 multiplied by negative 2.9 minus 1 to the power of 2. I got negative 31.2. So negative 31.9, sorry. So almost 32. You can see that the differences now are going by 0.2, 0.2, whereas previously we had greater differences. I'm going to give negative 3 another try, so that's negative 3 plus 5, and negative 3 minus 1 squared. That will give me negative 2, and then multiplied by 16, so that's a negative 32. Okay, so this is lower, so let's continue with negative 3.1. So this example, quite interesting. We're going to continue with negative 3.1 plus 5 multiplying negative 3.1 minus 1 squared, and we get negative 31.9 again. So it seems that at negative 3 is where we see that the function will have the minimum, the local minimum. And we're going to say that the local minimum will be at x equals negative 3 and y equals negative 32. Now, for the local maximum, this time we kind of got a little lucky because you see the turn is made right on the x-axis at the x-intercept, and we know the exact coordinates to be x equals 1 and y equals 0. So now that we know the coordinates of local min and max, we can draw the graph with a lot more confidence. So we'll know exactly where the minimum is. And these are the main points actually that we need to show on the graph. So the min, the max, the x-intercepts. And the minimum is at negative 3 and negative 32. So negative 3, negative 32 will be somewhere in here. And with a nice smooth curve here, we're going to connect all these points and draw our beautiful graph. And this would be the graph of our function. Don't forget to draw arrows at both ends, as these are continuous functions for any set of real numbers. Now, lastly, we have to determine the intervals of increase and decrease. So we're going to start from the left side of the graph. You see the pen is going down, which means that's an interval of decrease. The x values in charge of this decrease are anywhere from negative infinity to negative 3, all the way here. So we're going to say interval of decrease will start from negative infinity to negative 3, and the function is also decreasing from 1 to infinity. So we're going to join 1 to infinity to this. And the interval of increase, we only have one interval of increase right here. And this would be from negative 3 to 1. So we're going to write that down. Negative 3, 1. Another thing we usually like to analyze is the symmetry as well. And in this case, you can see from the graph that there is no symmetry. So if the question on a test specifically asks for checking for symmetry, then we should. And this would be how we would graph the polynomial function g of x negative x plus 5 times x minus 1 squared. So